I'm Dorcas Dupe Oseni. Like I said, a student of space geophysics at the National Institute of Space Research. And we've had a wonderful 2 weeks so far with two of our space students and scientists coming to teach us about one thing or the other. We start from introduction, we talk about stars, we talk about the solar system. And today we'll be exploring something a little bit interesting. So, and like we always say in every class, it's so glad to see you all. Just ensure to unmute yourself when you're not talking and just keep professional behavior, but it is meant to be interactive. So if there's a question, just just answer. There is no wrong or right answer here. We are here to just ask questions and see how much of it we can actually answer. And if you can change your name, so I won't miscall another name, that'll be fine. And yes, if you have a notebook to note down something, that'll be perfectly fine too. Let's go straight into it. I've introduced myself already. I'm from Nigeria, and my research is on heliophysics. So heliophysics is another word for solar physics. So it's a study about the sun, about the activities of the sun, and a lot of things that are going within and how the sun is interacting with our planet, is interacting with the entire solar system. So that is what my research is about. And this is a picture of me in my school, and you can see the sun right there behind me. So what we do here is we study the sun and try to see if we can predict the behavior of the sun. So that is all we do. And so, like I said, we are here to make mistakes, have deep discussion, and even work out with more questions. Yep. So let's get started. First, we'll be talking about what is light. Last week, I remember Josiah said something about light year. Does anyone remember what that is about? Light year. What is the light year?
I wasn't here, but I know what a light year is.
Oh, that's nice. Okay, what is it?
It's how long a light takes to travel from one place to another.
That's good. So light year. So now, if you now add the word year to it, it's now how long or the distance that light travels in a year. So we have light, we have year, light year. So now we have the speed of light is 300 million kilometer per second. So at that speed, what is the distance it's going to cover in a year? That is what we call light year. So now we're going to we'll talk briefly about light itself. And I'm going to start with some questions. So where does light come from?
Light comes from the sun.
That's good. Anyone else?
Light comes from stars.
That's good too. Light comes from stars. Where else?
The moon.
The moon. Okay. All right. So someone has already mentioned that stars, light comes from stars. So the person has answered the second question. So what color is light?
Every color of the rainbow.
The color of the rainbow. That's a very good answer. Okay, so the last one, can humans emit light? Yes or no? Can anyone answer that?
Can you repeat the question, please?
Can humans emit light?
I don't think so.
Think so. Okay, that's a good middle ground. Josiah, can human emit light?
No, I won't say so.
Okay, all right. So those are just some quick questions to just keep us thinking, to get us thinking about light. I'm not going to answer any one of them, but we'll see if as we go on, we've been able to answer any of them. So Yusuf said something that light contains every color of the rainbow. So a lot of time when we think about light, we think of sunshine. Most of the time, we think about colors of the rainbow. So, okay, I would like to make a quick comment. Moon, for example, do not emit light. They actually reflect light. So they reflect light from the sun. They don't have intrinsic light being produced from them. So, and just like we have large range of light, intensity and all other things, there are lights that we actually can't see. There are colors you can't see. There are sounds you can't see. There are sounds that their two pitches that are too high or too low for our ears to even detect it. So also is light. So, but there's something called the electromagnetic spectrum. And light is just, the visible light we can see is just a small section of this electromagnetic spectrum. And light from the sun, from other artificial light from the sun, we call them natural light. Light from bulbs, we call them artificial light. And when we look at them, they are white light. But has anyone tried this before? Try to shine a light through a prism. Has anyone tried it before?
I have.
That's good. So you've seen this effect before. And if you have not tried it before, I will encourage you to do it. Get a prism. Prism is like a glass, a transparent glass. It comes in a lot of different shapes. It could be triangular like this one. It could be cubic, different shapes. And let's a white light, it could be a torchlight, or it could be the sun. If you're able to like focus it and let it pass through and project what comes out of that light onto a surface, you will see that light is made up of all of this color, even though it is white, but these are the things that are made up of. And here we are able to just group those colors into red, orange, yellow, green, blue, indigo, violet. Those are just 7 colors. But in reality, they're actually more than this because it's a continuous spectrum. So there are lots of color between red and orange. There are lots of color between orange and yellow. There are lots of just like that. So there are a lot of them, but as the limitation of our eyes can distinctly, identify a few of this. And now, so light travel in form of waves. And when they pass through prism, then we have this effect that you see here. So it is each of the wavelengths that light is made up of that produce these different colors of light. And you see that when light passes through this, you see that there's a form of bend, and this light sort of bend is coming from a lower direction here. And we see that a part of the light bends more than another part of the light. So that is what caused that separation to be able to happen. So different wavelengths, different color are able to bend differently. So here we can see that the violet is able to bend more and red bends less. So I don't want to go too much in detail, but I want you to try this at home and tell me if you are able to observe this. So the ones that bends most here are what we call the short wavelength, and the one that is able to bend more is what we call the long wavelength. Now, this is what we call the electromagnetic spectrum. And like I said, the visible light that we see just makes up a fraction. If you can see my cursor, you see where I'm trying to capture. It just makes up this small part of the electromagnetic spectrum. Then we now have a lot of other ones. We have from the radio wave to microwave to infrared to visible light. This is the visible light. Then we have ultraviolet, we have X-ray, we have gamma ray. And each of these have different wavelengths. So when we talk about wavelength, let's try to visualize it a little bit. So you can see this second row. It shows how long, like what is the length, approximate length of their wavelength. So for radio, we can compare that to that of a building. For microwave, we can say it's somewhere between size of an human and butterfly and like that. So now, some of these names might have sound familiar. So I would like to ask, do you know what each of these waves are being used for? Have you ever had an encounter of, you've learned it in one way or the other, what radio wave is used for, what microwave is used for? I'm sure at least this one sounds familiar. Infrared or any of this. Does anyone know?
I cook with microwave.
Okay, so microwave helps you to cook your food. It helps you to make your popcorn. That's good. Which other ones? Anyone? Pikayo, Itsu, and yes, anyone can answer. Anyone, and any of our senior scientists.
Is X-rays used to check bones?
I didn't hear that.
Is X-ray used to check bones?
To check holes.
Is
to check
it?
bones. To check bones in the hospital.
Okay, burns. Okay, yes. So yeah, so X-ray is used by doctors when, for example, maybe you go to your dentist and they want to take an image of your teeth. That is what they use. They use the X-ray. And if you traveled at the airport, you see that sometimes they pass your bag through something. They pass it through something called X-ray. So it's able to see through your bag and see if there is any suspicious anything inside your bag. That is X-ray. So okay, I will just quickly mention what are the other ones for. So radio, I'm sure we all watch TVs, right? Television, we have radio at home. Okay, I used to have radio at home. I don't know if people still listen to radio now, but it is through radio waves that our radios and TV are able to capture signal. So they're able to capture signal and then they transmit it to us, and then we can hear and listen to whatsoever someone is saying in thousands of kilometers away from us. And so we have the infrared, which is used by night googles. So there are some googles that if you put on at night, you can see some distinct features and it will just be pitch black, and some other ones like that. So yeah, okay, so this is a bit of the explanation. So we have the gamma ray, which is used in medicine for killing cancer cells. Now, okay, so now that we've explored light and the different colors of visible light and the different electromagnetic spectrum, now let's delve a little bit into what the sun is. So what is the sun? And the first thing is, how does the sun looks like in visible light? So this image was captured by a telescope. We have it at the Big Bear Solar Observatory. Let me show the picture here. Yes, that is the observatory. So it's captured this picture of the sun. And does it look like the sun? When we look at the sun, there's a kind of color we expect to see, right? Do you think this is the sun? Do you agree?
I think it looks like a white dwarf.
Yes, that's good. So it looks a little bit strange. This does not look like the sun, but it is the sun. So they are different. We can observe and capture our sun at different lights. And with that, we can capture different features of the sun. So this was captured in visible light. So now the Big Bear Solar Observatory is an observatory. This is it's in another dimension that is in the United States, and it's able to filter the sunlight so that we can see the visible surface of the sun itself. So it filters all those radiation and everything from the sun. So what we are seeing now is the visible surface of the sun. And sometimes you can actually observe the sun with smaller telescopes. And so here are some of the solar telescopes. Then we can also use something we call solar filters, I think. So these are just handy instruments that you look through. Remember, you don't look at the sun with your naked eye. It's dangerous. Don't ever try it. So you use special objects like this, and it filters the radiation from the light so you can see just the visible part of the sun. So now the sun is white, and that means that it is made up of all these colors we have mentioned earlier. And I would like to push something. Why do you think the sun looks yellow? Can anyone answer?
Maybe it's the brightest thing in the solar system.
Okay, so
Or is it
the
the way
sun is,
it bends?
yeah, the sun is definitely the brightest in the solar system, but that is not what makes it yellow. So I'll give that as an exercise. I'll give that as an exercise to try to answer that question, and I'll ask again next week. Why does the sun look yellow? So because I think someone wants to talk. Okay, no. So because the sun is white, it produces all colors of the rainbow. So this makes it a white light. And this is just like every other stars in the universe. They produce white light, and when we filter it, we can see all colors of the rainbow like this. Now, if the sun is actually yellow when you wear a white clothes in an hot afternoon, then you won't be able to see white. It will look yellow. So these are the things that makes you know, are you standing under a white light or a yellow light? So, okay. Now, just some random question now. The sun is a what? Is it a blue light or
The sun
green
is
light?
I'm not very sure.
Is it, huh? I can't hear you. I missed that.
Is it a rainbow?
Okay, yeah. The sun is, that's an acceptable
It is a
answer.
star.
It is a star. Okay. And how many radiation wavelengths do we have from the electromagnetic spectrum I showed you earlier? Do you remember how many of those we have? Okay, if you cannot mention how many, can you mention one or two of those electromagnetic spectrum wavelengths?
Gamma rays.
That's good. Yeah.
Is
Then
it
there's,
8?
so we have 7. We have radio, we have microwave, we have infrared, and let's see. We have radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. So let's continue. All right, so I'll skip the rest of the question and we move on because of time. Now, remember I told you that depending on the wavelength at which you observe the sun, we can see different features. Now I'll show you a set of the same image of the sun, which was taken at the same time, but at different wavelengths. And you tell me, what do you notice? So let's start again. Look at this. This is the sun in a wavelength. This is the sun in another one. Another one. The same one, same picture. Same
It
picture.
looks like it's showing different colors, like rainbow colors, but not exactly rainbow colors.
Yes, that's right. So the colors are just to represent that we are showing the sun in different wavelengths. So it does not necessarily have different colors. But what I want you to look at deeply, I'll show it again, is do you notice any difference in the feature of what we are seeing? Apart from the color, do you see any other difference?
Emma, there's like a dark part in the sun or something like that.
Mm-hmm. Mm-hmm. But we didn't see it in other pictures, right? Like, for example, we can't see anything like that here, right? So these are the same picture of the sun, but when we observe the sun at different wavelengths, we are able to see different parts of the sun. Now here, for example, is a coronal lobe. We'll talk about that later. Here is something that we'll call coronal hole. But we have to observe it at this specific wavelength for us to be able to see it. So scientists, when they found out this, we've been able to, dig deeper into how the sun actually looks like at different point in time. So now let's go inside the sun, and I'll use a quick analogy. Does anyone here eat pasta? I think we call it spag in Nigeria. They call it pasta in some other region. Does anyone eat that food?
Yes, ma.
Okay, yeah. So personally, I enjoy eating pasta. I enjoy eating spag. So let's assume there's pasta in a pot on fire and you're cooking it. So we have the pot actually has a very thick bottom. The down part of the pot is very thick. Then you have a burner, maybe a gas or a stove, if it is firewood, that's fine. That is supplying something into it, it's supplying heat, right? It's heating the bottom up. Then we have the bottom that is very thick. Then inside the pot, we have water, we have, all the ingredients. Then we have the spaghetti, pasta. Okay, I'll use it interchangeably, right? Inside the pot, then we could see that at some point in time, it's as if those spag wants to jump up out of the, they're forming like a curve. If you look at my cursor here, they're like coming out of the pot, coming back inside, coming out, coming inside. So I want to use that now to, and let us compare with the sun. So the sun has its core, which is where the heat is generated from. And that is like your burner, if it's your gas or your stove, where the heat is coming from. That is the powerhouse of the sun. It's where the fuel is being generated that powers the whole system. Then we now have this region that we said it's the thick bottom of the sun, of the pot. The place is very dense, right? It's very thick, and it takes time for that place to heat up. It takes time. So, but it's still at the end, when it heats up, it's still able to transfer heat into what? The higher part of the pot. So this thick part is like the radiative zone. It's like the radiative zone. So it transfers heat through something we call radiation. You will learn about that in your physics class, or when you get to SS. If you're in SS already, you might have heard it already. So then from here, then the water also gets, begin to boil up. Then that can be likened to the next region of the sun where it is convective. So that place is less dense. The water is not as thick, as dense as the pot itself. So that place is less dense. There's not, and the temperature there is even much higher. And from there, you can see that inside the pot, the pasta are kind of twisting sometimes, and then sometimes they kind of come out. They want to liken that to magnetic fields inside the sun. So due to the sun being a huge ball of plasma, do you remember that from your first class? That the sun is entirely made up of plasma. So with the movement of the plasma, it generates magnetic field. And these magnetic fields, they are all over within the sun, and sometimes they pop out of the surface. As you can see here, they pop out of the surface, go out and come in. And magnets are north and south pole, right? Positive, negative, that's how we represent it. So just like that, and sometimes they also get twisted. Just like you have your spag in your pot that sometimes get twisted, those magnetic fields also get twisted. And when those twisting happens, they cause a lot of things. And those are what we like to term the solar activity, or we call them magnetic activity. Now, let's look at it from another perspective. So here again is the core, here is the radiative zone, here is the convective zone. Then we now have the outer layer of the sun. We have the photosphere. The photosphere is the visible part of the sun, the visible layer of the sun. And we have the chromosphere and we have the corona. Just like the earth has atmosphere, the sun also have atmosphere. And the atmosphere of the sun is called the corona. So it's just like the surrounding the atmosphere. But the surface of the sun itself is called the photosphere. So the words might be a little bit too big for you now, but just note the one you can note. The corona is the atmosphere of the sun. That is very important. The inner part is the core. Then the visible layer of the sun, just like, when you're on Earth, where you can stand, we can't stand on the sun anyway. So that is the photosphere. So now let's look at how magnetic the sun is. When I said the sun is magnetic, does that mean there's a magnet inside the sun? Do you think there's a magnet inside the sun?
No, ma.
No. So, like I mentioned earlier, the sun is made up of plasma, right? And plasma are charged particles. So when they move, as they are moving within the sun, they are generating magnetic field. And sometimes those magnetic fields, they penetrate out of the surface of the sun, forming what we can see, and it looks like a loop, right? So it forms this sort of loop. And we don't actually see magnetic field lines when we look at the sun, but we see this. Can you see this color? This is the sun in an ultraviolet image, but we see these loops around the sun. It is the corona of the sun following the path of the magnetic field. So what we are seeing here is not the magnetic field line, it's the corona, the atmosphere of the sun, forming a loop around the strong magnetic field of the sun. And this is very, very interesting. And now, not just the sun is magnetic, the earth is also magnetic. Do we know that?
Yes, ma.
Yes. So, and we also have something called, we also have the North Pole and South Pole. But the North Pole and South Pole is different from the geographic North Pole and South Pole. So Earth has, in fact, a lot of North Poles. It has the magnetic one here, which you can say this is the North here. If you can see my cursor, then we can say this is the South here. Now, because of the magnetic activity of the Earth, then something is generated around the Earth. So the magnetism is generated within the core, but now it produces something around the Earth itself, which is called a magnetosphere. Magnetosphere. So this is an artist. So an artist visualize what this will look like. And this is an artist visualization of what the magnetosphere looks like. So the magnetosphere acts like a shield. You see, when soldiers go in battle, they hold their shield to defend, whatever is coming, if it's arrow or dart. So that same way, this magnetosphere is our shield. It protects us from other dangers that are coming from within the solar system or even from outside the solar system. And what are those things? The sun is always releasing a lot of stuff. So we'll talk about that as we move onward. It releases a lot of charged particles. It blows something we call solar wind consistently. And if it penetrates into our atmosphere, it's dangerous for us. So our magnetosphere is like our cover. It shoots us from those things. And but there's something you can see here. Can anyone see this place and this place? This place, there seems to be a space here, right? Can we see it?
We can't see your cursor, your mouse.
Oh, you can see my cursor. Oh, that's good. Can you see now? Can you see my cursor now?
No,
No.
ma.
Oh no, I thought you could see my cursor saying. Oh, okay. Let me try to share my screen again so I can show you what computer is stopped. Okay, you can see my screen, right?
Yes.
Sorry, I can't see your screen.
You can't see anymore. Let me try. I'm going to stop sharing and share again. Equality. No, Wrong screen. You're seeing the wrong screen, right? Can you see now? Can you see my screen?
Yes, we can see your screen and we can see your
And you can
cursor.
see my,
also.
oh, that's good. How about when I put it to full screen like this? Can you still see my cursor?
Yes.
Yes, ma'am.
Okay. Okay, that's good. So I'm pointing to this part. Can you see now? There seems to be a sort of hole here, right? Can you see now?
Yes, ma.
So we call this place like funnel. So even though our magnetosphere shields us from charged particles and other dangerous things that could come from the sun and from our environment, there's still, it's not 100% perfect. So we have some path like this one where those particles can penetrate. So once they're able to enter here, you can see this, then they can also penetrate into this region and they get deposited into our atmosphere. So there's a certain region of our atmosphere that is called the radiation belt that contains very energetic particles that when we want to fly spacecraft into space, we are always very careful of that region because if not, we could lose our spacecraft there. So, but at least it's safe enough for us, and it has been good so far. So, just some quick question again: what is the Earth's shield called? Does anyone have an answer? So what do we have here? Can you see this?
Magnetosphere.
Magnetosphere. So the Earth's shield is called magnetosphere. Do you remember what the visible part of the sun is called?
My is it corona?
Corona is the atmosphere. There's another one. The
Is it the front layer, the foot?
Okay, that's a good attempt. It's called the photosphere. The photosphere. Okay, so last question. What generates magnetic field within the sun? Anyone remember?
This parallel or something running through the sun that makes magnet.
Okay. Yeah, I think I could pick up a few things of what you said. So it's the charged particles that are moving within the sun. As they are moving, they generate magnetic field. So, yep. So I want us to take, so we are not going to be able to take 5-minute break, but we're going to take like a 1-minute break. Just you can stand up, stretch yourself if you want to get a cup of water, and then we continue. So just a short break, and we continue again. I want to take my own water. All right. So are we here?
I'm back.
Okay, that's good. So now let's talk about some of the activities that goes on the sun. Now, remember when I was showing you those series of picture earlier, someone said there's something that looks like dark spots on the sun, right? That looks like, why is those places darker? And there are a lot of different forms of dark spots that we see on the sun. But we want to look at the first one, which is one of the most important ones. which is called sunspot. So this region of the sun, let's look at this video. So this was captured in 2017 by a NASA spacecraft. It was taken over a period of the time because you remember the sun is rotating, right? So we can see this dark spot of the sun being viewed in another wavelength, like we mentioned, and you can see how loops of magnetic field is coming out from that same area. I'll play this again. So this is what we call sunspot. And the sunspot is a dark region of the sun that is a little bit colder than its surroundings. It's a little bit colder than its surroundings. And why is it colder? Let's look at this picture. Now, we have magnetic field coming out from within the sun. And this region have a very strong magnetic field in this form of loop. And they trap some plasma around here. And when they trap this plasma, the magnetic field is still penetrating down deep into the sun. And in the chromosphere, in the layer below the visible layer of the sun, they tend to serve as an obstacle, preventing it to be transferred from the inner part of the sun to the next layer. So let's imagine that pot of spike now, and we are able to put a cover somewhere in the middle of the pot, and it reduces the amount of heat that can go to the next layer. So because of the strong magnetic field, it reduces the amount of heat that can get to the surface of the sun. And so those places become colder and also darker. But even though they look small, when you look at this video, even though they look small, they're actually really, really big. If you want to compare with the size of the Earth, for example, a sunspot is bigger than the entire Earth. So if they look so tiny, but they're actually really big from our own perspective. Now there is another interesting thing that also comes out from the sun, which we call solar wind. When you go out in the evening or during a windy day, you feel the wind in your face, maybe it's even blowing your hair and things like that. We also have these continuous streams of wind from the sun that blows in all directions. Let's say this, blows in all directions. So this is what we call solar wind. And they move at about 400 kilometers per second. The thing is, thanks to our Earth's magnetosphere, we would have been feeling those solar wind on Earth too. But because those solar winds they contain particles that are actually dangerous to life, so our magnetosphere shields us from the solar winds that are consistently coming from the sun. Now, where are these solar winds coming from exactly on the sun? Are they just being blown from the entire region, or they have a particular place where they're coming from? So let's look at this. They are coming from a place called coronal holes. Coronal holes. This picture is, I like the picture so much. It was taken just last month, actually, October 2024. This picture was taken, and it looks like the sun is smiling at us, the eyes and the mouth, same as if the sun is smiling at us. But it's actually not smiling. So these coronal holes are just temporary region of cold. So the atmosphere of the sun, those areas that are just cold momentarily, just temporarily, they look darker, just like the sunspots, but this is different. So that is where solar winds come from, according to science as at now. That is where they actually come from, and they emanate all through the solar system and into the heliosphere. Now, let's ask a quick question. What defines a day on Earth? Can anyone explain? What makes a day on Earth?
Mine's like 24 hours from the rising of the sun to the setting of the sun, then the rising of the moon to the setting of the moon.
Okay. That's good. That's good. Good answer. Does anyone wants to explain anything different from that? What makes a day on Earth? Okay, I think
that.
what did you say?
Please, can you repeat that question?
Okay, what makes a day on Earth? How do you define a day on Earth?
You find it when it's day, it's light. When it's night, it's dark.
Yeah. So when the sun rises in the morning, we feel like, oh, the day has begun. And when the sun sets, we're like, okay, the day is ending. So we define a day on Earth by the rising of the sun and the setting of the sun. And now, what do you think a day on the sun would be like then? What would it be like?
It would be hot.
Okay. So what I'm trying to ask is there night and day on the sun just like we have on Earth? So how do we define a day on the
There's
sun?
no night and day.
Okay. So now, how do we actually define a day on Earth? So I will explain a little bit. We actually define a day on the Earth by the rotation of Earth. So Earth rotates along its axis. So you know that it's not actually the sun that is rotating around us, right? We are the one, moving around the sun. All the planets, they are moving around the sun. So as the Earth rotates, as it comes back to the same spot where it starts from, that's what makes a day. So also on the sun is also rotating, but it takes a longer time for it to rotate. So when the sun starts rotating, when it comes back to an original position again, from the person that is observing, then we can say that is a day on the sun. Do you understand? So let's look at this, for example, this image that is moving and moving now. So let's say we observe something around here. I can't pause this, but let's imagine I pause this and we observe something here. Now, when the sun rotates, and you can see my cursor, right?
Yes.
Okay, so when the sun rotates and comes back, and we can see that same thing again we observe. Okay, let's pinpoint on this one, this shiny one that is moving very fast. When it comes back to the same point where we observe it, then we say that is a day on the sun. Do you understand?
Yes.
All right. So now, but there's one interesting part about the sun. The sun is not solid like our Earth. The Earth is solid. We can stand on the Earth, but we can't stand on the sun. The sun is made up of plasma, like we all know. So that means it does not rotate the way Earth rotates. So, for example, take a maybe a bottle or anything solid, or a ball, for example. Take a ball and try to rotate it. What do you see? All the parts of the ball, they rotate together, right? They are together. But if it's possible for you to take water and try to rotate it, you'll see that all the parts will not rotate together. And that is what happens on the sun. Different parts of the sun rotate differently. So when we are at the middle part of the sun, like here, there we have the part rotate faster than when we are at the North Pole or at the South Pole of the sun. So at the equator here, we have 25 days, actually makes a complete rotation. Then at the Northern Pole, we see that it takes 35 days for a rotation to be made complete at this pole. So depending on where you are on the surface of the sun, that's what determines how long, what we call a day, how long it is. So this is what we call the differential rotation of the sun, because different parts of the sun rotate differently. They do not move all together. They do not move all together. So it's be like some part is overtaking another part, something like that. Yep. So quick question. What are dark spots on the sun called?
Are they called sunspots?
Sunspot. That's good. And how long does it take for the sun to rotate around its axis?
25, 28, 26 days to 38.
That's good. So it could be 25, it could be 26, it could be 38, it could be 31, it could be 35. But on Earth, we know it's 24 hours, no matter where you are, right? So, yes. So now we have these two very, very powerful guys that we want to talk about. Remember when we're talking about sunspots, we call them the dark part of the sun, right? They look dark, they are colder. But do you know that these places that are dark and cold, they are like a corporate. You know, when you say something is a corporate, it causes something bad to happen. So they're like the chief cause of the most powerful eruptions from the sun. So you can see, before I play this video, I think you can see this loop coming out from the sun. I explained earlier that they are magnetic loop. So when magnetic lines come out from the sun, sometimes they twist, like I mentioned earlier. And when that twisting happens, you know you have a rubber band, right? If you take a rubber band or anything that is elastic and you twist it and you twist it and you twist it, at one point it will break, right? Can you hear it?
Yes.
Yes, mine to break.
It will break. So when it breaks, then a part is detached from one part. So that is what happens. Now let's look at this short video, which is on an eruption called solar flare. Now, solar flare releases millions, I can't even pronounce this number. This is 10,000 million, billion, I don't know. If you can pronounce it, please help. So they release a lot of energy into the solar system. And scientists notice that if we can actually capture all of this energy, do you know that we'll be able to power the whole world for about 20,000 years? So that means for the next 20,000 years, we won't need electricity. We don't need water producing electricity for us if we are able to capture energy from just one solar flare. And you can see this video as it's coming out from the surface of the sun. The loop is forming and it's getting bigger, it's glowing, it's shiny, and this thing is slowed down so that we can observe with respect to Earth. But in reality, when this occurs, when this is released from the sun, it takes just 8 minutes for it to get to Earth. It takes just 8 minutes for it to travel all the way from the sun to the Earth. So as you can see, it looks very slow, so that we can observe it from our own, at our own pace. Now, there is another one that's even worse than solar flare, and we'll call it coronal mass ejections. Have you heard of volcanic eruption before?
Yes, ma'am.
Yeah. So coronal mass ejections, we can liken it to volcanic eruption, except that they are million times greater and much more powerful than volcanic eruptions. And these solar flares, sometimes they cause coronal mass ejection to occur, and they release plasma from the sun. They release it into the atmosphere, and it travels all the way down from Mercury to Venus, Earth, and sometimes it travels to the edge of the solar system to show how dense and powerful these things are. But for this one, it takes a longer time to actually travel. If we want to measure how long this takes to reach Earth, it will take about 2 to 3 days for it to actually reach Earth. And the solar flares and coronal mass ejection, sometimes they are very powerful, sometimes they are not very powerful. So sometimes we have A class, which is the least class, Then we have the X class, which is the most powerful class. So when we observe them with our spacecraft, we can tell that, oh, okay, this is A class. So if it happens to reach Earth, then we are not even bothered. But if we see an X class being released from the sun, and it's coming towards Earth, then you see scientists, they sit tight. They are very, we are being watchful and careful and see if we need to prepare ourselves for this thing that is coming. And these ejections, these eruptions are controlled by something called solar cycle. So now, this is the same sun, but observed over the years. What is the difference? If you can see my cursor, what is the difference between the 1996 sun and 2001 sun? Just tell me one difference.
It looks like it's becoming bigger and glowing brightly.
Okay, so the size is just is not real. The size difference is not real. It's just so that we can put everything together in this whole picture. So, but you mentioned two things. You said it's becoming brighter. So that is the correct answer. So in 1996, we could say that the sun was not so much glowing bright, but as it is moving, what happens as it gets to around 2002, it's so bright. Then as it's going again, as it gets to 2006, what happened? It looks like it's not so bright again. Then again, the cycle continues. It starts becoming brighter and brighter again. So this is what we call the solar cycle. So the sun undergoes a period of minimum activity whereby there is not so much going on around the sun. And then it gets to a point of maximum activity where there's a lot going on around the sun. So now, for example, you know, the solar flare and CME we talked about here, these ejections. Now, sometimes during the minimum activity, you can maybe observe one in a day, one in 5 days, maybe one in 10 days. But during the time of this maximum activity, we can observe 3 of them in a single day. So it affects and determines how those things occur. Now, scientists were able to plot this into a graph and to observe how does this actually look like. So now this is a plot of the sunspot. The sunspot, as you can see here, this is the solar minimum, this is the solar maximum. Sometimes it's very low and we can't see, you know, a lot of sunspots, and sometimes we can see a lot of them. So when we see a lot of sunspots, we know that that's a lot of activity from the sun. But when we can't see a lot, then we know that, okay, the sun is calm. So let's call it the calm and the energetic sun. We have the calm sun, we have the energetic sun. Now, I want us to look at the journey of a solar eruption. Something happens from the sun, then it travels down to it. Let's look at this video.
Magnetic fields inside the sun. In some places, strong magnetic fields push their way up through the surface. They slow down the eddies of hot gas. The surface cools and darker sunspots appear. The electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band, and then the rubber band breaks. Several billion tons of plasma is hurled out from the sun. This is called a solar storm. The solar storm can reach speeds over 8 million kilometers an hour. After 6 hours, it blows past the planet Mercury. After 12 hours, the planet Venus. And after 18 hours, the solar storm reaches Earth. When the solar storm reaches our planet, something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm.
I want to quickly explain what is happening here. remember, this is our magnetosphere, right? And this is that plasma that was ejected from the sun. Now, can you see something? You can see that there's a sort of arrow that we use to represent it. So we have the magnetic field of the Earth pointing upward, right? And we have the magnetic field inside the plasma that is coming from the sun pointing downward. So when these magnetic field lines are pointing opposite, one is pointing upward, one is pointing downward, it gives room for a reaction to occur. So when that reaction occurs, that is when the penetration I mentioned earlier happens. So let's see now.
The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole.
What do you think is entering into our head now? What is that?
The sun radiation or something like that.
Yes, radiation, particles from the sun. That is what is penetrating. Now you can see that it has done something to the front part of the Earth's magnetosphere. It has already penetrated, right? Now it will go to the back again of the magnetosphere and do the same thing.
This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
Now, this is what causes aurora. And I'm sure a lot of us have not seen aurora. Personally, I've not seen one myself. And I always say I want to see. So these are some of the effects that we see here on Earth. When those plasma are ejected and they react with our magnetosphere and those particles penetrate, they react with our atmosphere. So there's a lot of chemistry going on there, which I will not explain, but you get to understand later on. And that is what causes this aurora.
Gas.
Oh, okay. Repeated. Let's see if we can see how this aurora looks like a little bit, which is very beautiful. Okay, not playing. Let's try again. So this is the way the aurora looks like, which is very beautiful. These aurora are usually observed towards the North Pole and towards the South Pole. So, Nigeria is at the equator. That is why we don't see it. So if you travel to Canada or you travel to some states in the United States, or you go to places like Australia, which are the southern, they are really, really down the map, you will be able to observe this thing. So these are some of the, effect of solar eruption, and you've seen how they journey down from the sun to the earth. So let's imagine these scenarios, these quick scenarios. So let's say on a good day, you wake up and in fact, you can't even listen to news because the television could not connect to any channel. There's a power outage in countries and continents, and airplanes could not even fly, and maybe ships could not even move. What do you think could cause this thing? Is it even possible? What do you think could cause it? Can anyone answer?
Ma, can you please repeat what you just said?
Okay, so let's look at, you can see the pictures on the slide, right? So let's assume on a beautiful day, then suddenly power went out across countries and continents, and your TV is not even connected to, stations. TV could not connect, airplanes could not fly. You could not even use Google Maps. If you know what Google Map is on your phone, you could not use Google Map to move. What do you think could cause this? Like all this just happened at the same time. What do you think could cause it?
Maybe the radiation is strong that is affecting the electronics and the sea and the air.
Very true. Does anyone want to try? I think a lot of people have not spoken here. Pikayo, are you there? Isuf, do you want to try? Oh, there are a lot of other people here. Does anyone want to try? What do you think could cause it? I want to hear your voices. Anyone else?
Okay, someone is raising their hand.
Yes. Go ahead and talk.
I think because something on space has effects on the Earth and other
Yeah,
solar planets, which
yeah,
causes these things that happen, like not able to watch a channel, or not able to fly plane, or not
yeah.
able to sail through the sea.
That is very correct. That is very correct. So something could happen from the sun and could have affected all these things together. And so I actually put in some options here. Could it have been a terrorist attack? Or was it an alien invading Earth? Or was it an earthquake or tornado or hurricane? Nah, it's not any of this. It's the sun that is able to cause that all at the same time. And that is why we have space scientists that are trying to like understand the sun, want to be able to understand its behavior. So that if something like this is about to happen, we can do what? We can protect ourselves, we can guide ourselves. And we have a lot of mission already. These are just some of them. We have a lot of mission in space already. This is Parker Solar Probe. Okay, I will tell you something. This is the instrument that I use for my research. Parker Solar Probe is the closest instrument to the sun. That is, out of all the spacecraft we have launched to the space, is the only one that have come that close to the sun. It actually touched the atmosphere of the sun, which is the corona, if you remember. So yes, and we have a lot of other ones in our magnetosphere, so that I want to understand a lot of other things. Then we have some other ones on places like Mars. This is Mars here, and the down corner, and some other ones. I think Josiah showed us last week the rovers on planet Mars, and we have a lot of other ones. And I want to tell you that even though they look so plenty, like, oh wow, we have a lot of spacecraft in space, we actually don't have a lot. The distance between Earth and Sun, does anyone remember how far Sun is from Earth? Or can you guess? If you can't remember, can someone guess?
100 kilometers or 500 kilometers.
Oh my God, multiply that by million. So
I
the
think
sun is
it's 4,012 light years.
huh. Okay, that's a lot. That's a lot. Can anyone else try?
100 million or billion kilometers.
Okay, I still want to see someone else want to try. Some answers are very close, some are very far too. Okay, so I would answer. So the sun is hundreds of million kilometers from Earth, like 100, 150, thereabout 150 millions of kilometers. So just imagine the millions of kilometers, and you just have like 27 spacecraft or something within that space. So it's actually nothing compared to the entire space that we have out there. So with these spacecraft, we are able to observe the sun and track its activity. So now we're supposed to do some quick mathematics, but because of time, I will just do one of them, just one of them, and then that will be the end of today's class. So I want us to assume the job of a space scientist now. So all of us here, if you have attended this class from beginning to now, you're already a space scientist in a way. So we want to perform some space mathematics. So let's assume that, are we ready? Let me see if I'm not alone. Are we all ready? Do we want to do some space mathematics?
Yes, ma'am.
Okay, I only heard one yes. Yusuf, are you ready? Fikaya, are you ready?
Yes.
Who else is there? Okay, I've forgotten your name. I've forgotten your name. Can you remind me?
Lily.
Lily, yes. Lily, are you ready?
Yes, ma'am.
Okay, so let's do some space mathematics. So there are a lot of questions here, but I think I will just take one or two of them. So now, on November 2004, the sun released a very powerful X-class flare. Remember, we said we have A class, we have B class, we have C class, we have M class, and we have X class. And X class are the most powerful of all of them. So on November 7th, the sun released an X class, which is the most powerful one. Now, this X class also caused a CME to erupt. So there were two things that happened. There was a solar flare and there was a CME. Now, on November 9th at 12 o'clock, a storm began on Earth. What we call a storm is when the ejection from the sun interacts with our magnetosphere. Then we'll call it that a geomagnetic storm has happened. When you see that video where you see the particles are entering into our magnetic field. Now, can we calculate the speed of the CME as it travels from the sun to Earth between November 7 and 9? So on November 7, there was an eruption. On November 9, we began to feel the effect on Earth. Can we do some calculation on that? So let's take a first one. I hope you are with your biro and pencil. I will not just show you the answer. I want you to actually try something. So the first question, how long did it take for the CME to arrive? I'll show you some of the parameters so you can quickly take a look. So we said the distance from the sun to Earth is about 150 million kilometers. You won't need that for now, but just look at the time. So it started around November 7 at 4:06 p.m. This is 4:06 p.m. if you want to convert it. And it arrived on November 9 at 12 o'clock. Can you calculate the difference between these two times? Can someone attempt that? How many hours or minutes difference is that? Anyone can try to. Anyone can try. It's not just for the students alone. Our scientists in the room can also try. Let's see how fast we can get that. Is the question clear? Hello, can you still hear me? Is the question clear?
43 hours, 54 minutes.
Wow, that was fast. Okay. Okay. Who's the next person? Anyone else?
52 hours, 6
Okay.
minutes.
Okay. That's good. Let's keep it going. Yusuf, I think it might be a bit hard for you. Are you able to try?
I'll try.
Okay, try. Just try. It can be a little bit, a little bit harder for you. Any other answer? Okay, so I'll show my answer now. And yes, let's see. It's 3 hours, 54 minutes. So how did we calculate this? Now we have November 7 at about, oh, there's a mistake here. This is supposed to be 4:06, not 4:00. So November 7 at 4:06 p.m., the eruption began, right? Then from November 7, 4 p.m. to November 8 is 24 hours, right? From 4 p.m. to 4 p.m. is 24 hours. Then from 4 p.m. on November 8 to 4 a.m. on November 9, that is 12 hours, right? Now, from that 4 a.m. on November 9 to 12 p.m., we have 7 hours and 54 minutes. So altogether, if you add them all together, we have 43 hours and 54 minutes. That was a very good attempt from anyone that attempted it. Sorry, I couldn't give you a lot of time to try it all. So there are a lot of other ones, but we're not going to try them. We're just going to end the class here and we go for questions. So there's some other question here, but we're going to skip it. And there are some exercises I want to give you. Okay, let me just mention this. So I want you to try this at home. There are some of our phones that actually has magnetometer. And does anyone have a compass at home? Does anyone have a compass at home? If you don't have a compass at home, try to download a magnetometer on your smartphone. And I want you to try to detect magnetic field in your house. Using that magnetometer or your compass, move close to certain objects and or structures and try to see if there will be a sort of deflection on your compass or on that magnetometer, and see how strong or weak the magnetic field coming out from them are. Is anyone going to try this?
Yes.
Yes, okay. I want to hear one more yes. Who else is going to
Yes.
try this? Okay, so that is a task. So I've heard at least 2 yeses now, and I want you to try this. Try to detect a magnetic field in your house, maybe from an object, from your microwave or your fridge or something. Just try it, and we'll hear back in the next class. So this is the end of the class. What have you learned today? What are the questions that we have? So let me hear. I'll stop sharing. And you can put on your camera, let's see each other and ask questions, whatever question you have. Are there any questions? Okay, so tell me what you have learned today. Tell me one thing that you have learned today, if there are no questions. Tell me just one thing.
I learned that the sun, the sunspots on the sun are cold areas around the sun. That the radiation is preventing it from getting hot, but if you later get hot, it's temporary.
Okay, okay. So to add a little bit to what Precious said, so we have sunspots and we have corona holes. So both of them look colder and darker, but sunspots are much more permanent than corona holes. So sunspots, because of the magnetic field that is very strong there, it affects heat, and those places now becomes a little bit colder and darker. And they're also responsible for what eruptions from the sun, right? The sunspots are responsible for those. Okay, that's a very good one. Any other thing? What have you learned? Yusuf, what have you learned today?
I'm a bit young, so I didn't understand everything, but I enjoyed learning about everything that I understood.
That's excellent. I like that. Okay, so you enjoyed it, and I'm glad you did. Okay, Mikhail, what did you learn? Are you able to talk? If you can't talk, you can try to type in the chat.
I learned that the rainbows are basically just made from the colors of the rainbows are discharges from light, and that light is what makes light that makes all of the colors, and you can't look at the sun with your actual eyes. You need a type of material to look at the sun because it's very dangerous.
Yes, yes, that's very good. That's really good. You must not look at the sun with your naked eye. It is not good. Actually, when scientists began to observe the sun early on, Galileo and some other people, when the telescope was just made, they were observing the sun just with the lens, like the natural lens, and it's actually affected them. Before, over the years, they now discover that, oh no, don't try to do that. So, and also that the white light is made up of all the colors of the rainbow. Even though it looks white, it's made up of a combination of those different colors. That's a good one. Anyone else? Lily, I don't know when you joined. Are you able to learn one thing or two today?
Yeah, a little bit actually.
Okay. So is there anyone you want to share with us?
Okay.
Oh, you're muted. Are you?
I learned how the sun is far away from us and how and the effect on how it can cause on Earth when it exposes that kind of danger to us.
Yeah, yeah. That's a good one. And I want to add to that that it's not thing for us to be afraid of. So it's not all the time that those things are coming towards Earth. So a lot of time, most of the time, the eruptions are going to other parts of the solar system. So sometimes they are going behind the sun. Just some of those times that they actually come towards Earth. And some of those times when they come towards Earth, they might not be so powerful to cause any danger, and just once in a while, when they are so powerful, they can affect our spacecraft in space, but they don't affect us so much here on Earth, except they are like really, really powerful. Okay, you're raising your hand.
I have a question.
Mhm.
Is it true that aliens are getting spotted on Earth?
Oh, aliens, please. When you see one, tell me their address. I don't know. Um, I don't know if aliens have been spotted, but I know that so far life has not been found anywhere else outside Earth. So we're trying to look for life outside Earth, but we've not found one. But a lot of time you see some strange things flying. In fact, I think Josiah and I, there was one of the astronomy workshop we attended, and we're making night observation. I saw some things fly, like the flying three objects flying in synchronized motion, like perfectly aligned to each other. And they were so high up there. They were not airplanes. I don't know whatever it is, but we tend to see those things a lot of times. And scientists call them UFOs, unidentified flying objects. So aliens, I don't know yet.
Secondly, are aliens dangerous?
Hmm. Okay. So now it depends on what. Okay. So let's take it from this perspective. When you see aliens being depicted in movies, they look like strange or with big heads, or they look. Nobody knows what life outside Earth will look like. We don't know. Maybe they will look like Earth, or they are just bacteria or organisms, or they're just animals. We don't know yet. So we don't know if they're dangerous or not, or we don't know. Yeah, there was actually a mission that is sent to space, Voyager, where the mission has gone past Pluto now. It's no longer in the solar system, and it's still moving continuously. So there's a picture of a man and a woman on it and some other things, that in case this spacecraft gets to a planet in the solar system, in the universe, and there is life there, they can know that, looks like some people also exist somewhere else. Maybe they'll reach out to us if they find a spacecraft, but we've not, nobody has reached out to us yet. Okay, Precious.
I also saw that they said that some of these spacecraft and stuff like all those UFOs, they are from clouds, like cloud formation. And I thought I was shade.
Yeah, yes, it's possible because we don't actually know what they are. It could be some cloud formation, something that's just moving, and you know, sometimes, for example, when people see comets, we talked about meteorites in the last class, asteroids and all, when they penetrate into our atmosphere. Some people don't know what it is. They might be like, oh, there's an alien flying in our sky, but they are just some space rocks that are penetrating into our atmosphere, and they're like flying through. Yeah.
Okay, I learned one thing today and I want to share. So I
Okay.
learned how the aurora, how they formed, and
Oh,
I'm
that's
looking
nice.
forward to seeing one day, maybe.
Okay. That's awesome. That's awesome. Who else have I not heard from? Precious, do you still want to talk, or No, I see you raising your hand.
The question.
Okay.
Ma, those cold spots, the sunspots, sorry. Ma, you said that they are permanent, and if they continue, would they affect the sun and prevent the heat from reaching us?
Okay, so now the sun itself is already like, oh, I think my network is, can you hear me?
Yes, yes, you can.
I think my network is glitching. Sorry about that. So now, hello. Hello?
We can
Ma, I
hear
can
you.
hear you, ma.
Okay, from my own end, looks like I'm glitching. So sunspots on the sun, they can actually stay there for days to weeks or months. So they're not like all like for years. No, they can be on the sun for
Ma,
like
I
days,
can't hear you
months.
anymore.
Okay, that's a problem. How about now? Can you hear me?
Yes, ma.
Okay, good. I'll put off my camera. Let's see if that makes it better. Sorry about that. Please, if you can hear me, say hello.
Hello?
Hello.
Okay, you can hear me. Okay, I'll just keep talking. My computer has stopped working, sort of. So sunspots on the sun, they just appear for like days, weeks to months. They are not like there for years, and they go and they show up again. And also, when we say they are cold, so that coldness is just they're a little bit colder. You know, the sun is very hot already. So the different the hotness of the sunspot itself, it's even too hot, is really hot, but it's just a little bit colder than the surroundings, but that doesn't mean it is actually cold. So you would see that picture of solar minimum maximum, where there's a place where the sun appears not to be so much glowing, and there's a part where it appears to be glowing so much. So in a way, we could maybe feel it a little bit in our climate, but not really much. Like we don't tend to feel that, oh, this year is really, really hot because the sun is hot, or because there's not a lot of sunspot. Then this year is very, very cold or very, very hot because there's less or there is more sunspot. We don't tend to feel it on Earth. It's just a very little change in how would I put it? What someone should borrow me an English word. A very little change. Like it's not very obvious that it affects our temperature here on Earth. Okay, so if there are there still any other questions or comments? If there are no other one, would round up soon now. Mr. Clement, do you want to add something? Did you learn something? Thank you, Lily.
Yeah, I did. I learned a lot. Yeah, it's just my first time joining the class, and
You're welcome.
yeah, at least I've learned some space terminologies. Thank you for the class.
That's good. Thank you so much for joining. So, Daddy, my dad is here. It's all the time for time saving. What did you learn? I don't know if it's here. Okay. So, as we finish, I would like to announce someone that is very, very important that is in our midst. Her name is Margaret Ikakwe. She's a space scientist. And please, Mark, do you have anything to share with us as we round up the class?
Sure. Hello, everyone. Sorry that I cannot turn on my video right now. Hi everyone, it's nice to meet you and hear from all of you. Today, it's nice to follow along the very interesting lesson that Dorcas has taken us through today. I hope you all enjoyed it, and I hope you all learned as much about the sun as I did. It was really enlightening for me. And
Yeah.
yeah. I'm not sure what else I have to say, but that's it.
If you have any question for a space scientist, this is the time to ask her. Ask her some questions. Like, what does she do? Okay, can you please tell us, Ma, what do you do? So they will understand.
Oh, okay. So I'm interested in the universe, the entire universe, as much as you all are. I'm sure that's why you're taking this course. But specifically, I'm trying to understand how the universe started. Okay, so we all know, we've learned so much about the sun today, and we know about the planets, the different planets. I heard people talking about aliens and so many other things. All of that is contained in our universe, and we, as scientists, we don't really know yet how the universe started and a lot about the universe's history. And so I'm trying to understand a very small part of the universe, the past of the universe. So very close to when the universe started. That's my area of research. I hope that makes sense to people.
Yes, you want to tell us how does the universe looks like when it just began? So I think Precious is raising up her hand. Do you want to say something?
Sure, go ahead, Precious.
Is it about the Big Bang? The beginning, I think that's how they said the Earth started.
Yes, that is really good. Scientists right now believe the universe started in a Big Bang, yes. But that's mostly all we know. We don't know a lot of the details about how the Big Bang really, like what brought about the Big Bang and how the universe has moved from that point at the Big Bang till today. So we're still trying to, we kind of know a few things, but we need to fill in the gaps here and there. That's what I'm doing.
Wow. Thank you so much for sharing this with us.
Thank you.
Thank you, Ma.
Yes, thank you so much. We're so glad to have you, and we'd like to see you again some other time. So we're gonna round up now, and so yeah, that's it. Do have a wonderful